All right, let's dive right into this explainer. Think of this as your ultimate examiner's playbook to absolutely conquer Cambridge AS and A-Level Computer Science Syllabus 9618. We're specifically targeting the notoriously dense topic 4.1 today. If you're currently prepping for this exam, you already know exactly how intimidating the von Neumann model and the stored program concept can feel, right? It's like this massive, dense web of logic, hardware theory, and super abstract execution sequences. But today, we are going to simplify the complex. We're taking that huge, overwhelming textbook and boiling it straight down. As you'll see, one powerful idea, when structured correctly, is worth 1,000 words of rambling exam answers. We're looking directly at what the Cambridge examiners actually want to see on your paper and exactly how you can deliver it perfectly every single time.
To kick things off, we literally have a quote from a senior examiner reminding us of the incredibly high stakes here. It says, "Mastering CPU architecture is essential because it appears in every single examination series. No exceptions. You can't skip it, you can't gloss over it, and you certainly can't wing it on exam day." The examiners are specifically targeting distinct cognitive domains here: your knowledge, your application, and your analysis. So we really need to learn exactly what examiners are looking for. Not just what the textbook says, but how they want you to actually prove your understanding.
So here is our roadmap for today's session. 1. Essential CPU architecture. 2. Mastering core concepts. 3. The procedural framework. 4. Top examiner warnings. And finally, 5. Critical evaluation skills. Let's get to it.
Section 1. Essential CPU architecture. The challenge: Alex versus Sam. We're going to start by looking at a real challenge facing two typical students who represent the two most common traps candidates fall into.
Okay, check out their flawed answers side by side. On the left, we have Alex. Alex is our classic over-explainer. Notice this massive block of text. Sure, it's completely overloaded with raw CPU facts and vocabulary, registers, buses, memory units, but it totally lacks structure or analysis. It's basically a data dump that scores 0 marks for application. Why? Because Cambridge's academic benchmarks require logical, structured reasoning. Then, on the right, we have Sam. Sam completely panics. By rushing and missing the command word entirely, completely ignoring the difference between a word like describe and evaluate, Sam fails to engage the right cognitive domain. The assessment framework heavily prioritizes analytical depth, and honestly, neither of these answers has it.
Moving on to Section 2, Mastering Core Concepts. This is our big theory and strategy reveal. Let's set up our theoretical foundation before we jump into how to apply it.
The von Neumann model and the stored program concept are the absolute fundamental principles of topic 4.1, but pay really close attention to this requirement here. Cambridge explicitly demands that top-performing students demonstrate mastery by transferring these concepts to completely unfamiliar exam contexts. Let that sink in. Memorizing the fetch-execute cycle from your notes just isn't enough. You must apply it to bespoke, specific scenarios that the examiner literally invents for the paper. If you only memorize the textbook definition, you are going to fail the application phase.
So how do we actually bridge that gap? Well, top students structure their answers using something called the Peel framework to guarantee that deep analytical depth. Here's how it works. P is for point, state your core concept clearly right out of the gate. E is for evidence, provide the specific technical detail or data from the scenario they gave you. The next E is explanation. Logically reason out how that concept applies to the evidence. And finally, L is link. Tie the whole thing directly back to the specific command word in the question. Implementing this framework completely prevents the dreaded data dump and forces you into logical, structured reasoning.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, Section 3, the procedural framework. Think of this as your blueprint for transformation. Let's see how this builds into your computer science success blueprint, shifting you from raw theory directly to exam application under strict time pressure.
Here is the exact 5-step systematic sequence you must use to tackle those complex 4.1 exam questions. Step 1. Deconstruct the question. Figure out exactly what that command word is asking. Step 2. Extract relevant data directly from whatever unfamiliar context they've thrown at you. Step 3. Select your analytical framework. Ask yourself, is this a time complexity issue or maybe a hardware limitation? Step 4. Execute with clear notation. Show you're working. And Step 5. Present with correct terminology. Following this exact standardized sequence inherently verifies your results and fits the examiner's rubric absolutely perfectly.
Now watch this transformation. It's brilliant.
The original flawed attempt on the left was super vague, with no clear methodology. But by actively applying our 5 steps and layering in the Peel framework, the new answer on the right zeroes in on the key elements. It applies the relevant principles of the stored program concept. It executes the analysis with incredibly clear working, and it justifies every decision with hard evidence. Just like that, we've moved from superficial breadth to profound analytical depth. We're turning those red marks into green check marks.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Welcome back. Let's get straight into Section 4, Top Examiner Warnings. We're starting an interactive workshop right now by looking directly at the biggest pitfalls drawn straight from the Cambridge Principal Examiner reports.
So, the senior examiner explicitly warns us that students consistently lose marks for 3 massive failures. First, answers are way too vague. You literally cannot just say something like, "This CPU processes data." You absolutely must use specific technical details regarding buses, registers, and memory units. Second warning, students forget to check boundary conditions and edge cases when analyzing algorithmic implementation. And third, answers are not specific to the given context. Look, if the question is about a washing machine's embedded system and you give a generic answer about a desktop PC, you score 0. You must link the von Neumann model to the specific scenario they provide.
Now this brings us to a crucial point, a real game changer, the method mark strategy. Examiners actually award marks for process, meaning your systematic working out and your clear notation act as your ultimate safety net. Even if your final calculation or algorithmic output is dead wrong, showing your step-by-step decomposition can completely save your grade. Never, ever erase your working out. Let's put this to the test. Take a few seconds right now to mentally scan the data on screen. I want you to identify the exact sentence that loses marks for failing to provide specific technical evidence. Try to find the flaw in this sample CPU architecture paragraph. It might sound okay on a casual read, but remember what we just learned about the Peel structure? It needs evidence. Spotting these weak points in a sample is exactly how you master spotting them in your own writing.
All right, Section 5, Critical Evaluation Skills. This is the final system. If you want to separate an A grade from all the rest, we have to elevate our critical analysis to effectively evaluate algorithms.
Top-scoring candidates constantly demonstrate evaluative thinking by considering multiple solutions and analyzing trade-offs. You have to weigh these 3 exact factors. First, time complexity. How does this impact execution speed and overall efficiency? Second, space complexity. What are the strict memory usage constraints here? And third, edge cases. How does the system maintain stability at those tricky boundary conditions? You need to acknowledge limitations and justify your trade-offs across these 3 specific columns.
So, bringing it all together, our complete cheat sheet boils down to these 3 golden rules that essentially guarantee top marks when you combine them with algorithmic thinking and rigorous testing. Rule 1. Command word decoding. Don't start writing until you know what cognitive domain is being tested. Rule 2. Peel framework application. Point, evidence, explanation, link. Use it every time. And Rule 3, the time management matrix. Always allocate your time based on the method marks available, making sure you always show your clear working.
Here is the reality. Students who actually implement these computer science strategies see an average improvement of 2 grade boundaries. That is huge, 2 whole grades. But let's be real, that only happens if they practice consistently with our weekly explainers.
Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams, your Cambridge success starts here.